The views expressed throughout this podcast are solely those of myself and the guest and do not necessarily reflect the views and opinions of ATCC or any other institution. Hello, and welcome to Behind the Biology, brought to you by ATCC. I'm your host, Dave Yarmush, and this is our second episode in our series with Neely Chakraborty, Head of Cryobiology Research and Development at ATCC. Once again, if you haven't listened to the first in the series, I recommend it because we've deviated from our normal lineup, and most of the personal aspects of Neely's story are there. Today, however, we shift our focus to ThawReady cell technology, which is designed to reduce cell injury during the freezing and thawing process, while ensuring cells are ready for use immediately after thawing. Welcome back, Neely. Today, like we said last time, we're going to be talking more about the ThawReady cells. Based on what we spoke about last time and what I've come to understand, this is an increasingly significant component of modern cryobiology. From the name, it seems reasonably clear that the product requires some amount of less preparation for use, which saves time and effort. So how does that work? Honestly, can you just expand on that?
Sure. So to give you a background, right, when you cryopreserve, generally you do that in presence of a cryoprotectant. And what you do is that you expose the cells to a cryoprotectant and start lowering temperatures with a view to preserve the cells. As you are lowering the temperature, you are essentially drawing out water from the cells because you'll form ice first in the extracellular environment that draws out water, it dehydrates the cell, and then you keep lowering the temperature and you lower the temperature past the cryogenic limit, which is generally negative 80 degrees centigrade, right? And you keep doing that. And finally, when you hit liquid vapor phase of liquid nitrogen, you stop and preserve cells, right? What I just described is the common way to cryopreserve cells, right? Everybody knows about it. But if you think about it as a system, as a cellular system, you are taking the inner working of the cells through an excruciating thermodynamic journey, right? Ice is forming outside, the cell is losing water. So if you think about it, enzymes are losing their props, which are a water molecule, right? A lot of things are happening. All these injuries, I say use the word injury because these are unnatural things happening to the cell.
Mm-hmm.
And even those different molecules within the cell do not get to react because there is not much thermodynamic incentive for them to create any cascading reaction. But essentially, there is a molecular mechanism to remember these injuries, right? And they get manifested when cells are thawed. You may kill some cells because ice formed extracellularly, and some of the ice crystals might have injured the cells. But basic molecular injury that happens in the cell gets manifested after you have thawed the cell and you put them back in the culture. What happens is generally immediately after thawing, most of the cells you'll see, well, there are cells that look healthy and whatnot, right? They have membrane integrity. But then remember the injury they had? They start manifesting that injury. There are different theories there. Delayed onset of apoptosis happens, cells kill themselves. A lot of things happen. It is a little bit easier if you are working with a cell line because they will divide, and in a week or so you will get your culture ready to go, right? And you can you run an assay with the cells at that point. So generally, it'll take a week for you to have the cells to the level that they are ready to be used in your workflow. But this thawing part, immediately after thawing, your cells are not ready because they have accumulated injury during the freezing process. As simple as that. Now we started thinking about, can you do something differently so that when you are freezing, you are accumulating less injury with a view to have cells ready to be used right after thaw, essentially thaw ready. So that is the framework. This platform technology is very exciting for ATCC. It's a ATCC developed platform technology, and the first set of products are already out in the market. We went for one of the most difficult cell types, immunogenic cell types that are designed to react, right? If there are any injuries. And that's the entire background of that ThawReady cell.
That's fascinating. Especially that regrowth process taking about a week. Again, I'm not in this field, but my first thought when you were describing that was with the sheer amount of cell death, and you didn't attach a percentage to it, and I'm not sure how significant that is for my question, but what needs to be regrown are only the partially injured, partially maybe not survivor cells. I would have to imagine that's got some degree of an impact on the actual behavior of those cells post thaw, right?
Right. So those behaviors are manifested by less number of cells, poor post-thaw viability. You have, again, we need to, if you uncouple viability from function, essentially why you are culturing the cells, because you are going to use them downstream to capture some, to use them in some functional way to validate your assay, right? So that functionality, even though they are alive, their membrane integrity is intact. They have intact membrane, doesn't mean that they're ready to be experimented, right? That's another aspect.
Right. They may
So
not be operating the same way internally, expressing the
yes,
same genes.
yes, not they may not have the right machinery activated yet
Exactly.
because they're busy repairing their stuff that got injured. So that's the power of our ThawReady platform, that we have come up with a product that is, we within very short time of thawing, they're ready to be used because, quote unquote, injury, we were able to modulate the injury.
Sorry, I think I can only ask what I think are
Sure.
naive questions at this point. Um, is this concept of cellular injury as a consequence of freezing relatively new? Or, I mean, I guess what I'm asking is why weren't this kind of thaw-ready cells produced earlier?
Excellent question. Because as a field develops, the field expands, but there are obvious gaps that
Hmm.
remains, right? Those gaps create pain points, and if there are pain points that are really prohibitive in developing certain technologies, well, people will work around them, right? So prolonged culture of post-thaw cells, whatever survived, was an adaptive mechanism. Longer culture costs money, it costs, it is effort, right? And it is risky because you might contaminate things. Or if you are working with really injured cells, your functionality of the cells might be not there, right? So you might be operating on a different aspect. Earlier, we didn't have, I would say 20 years from now, we didn't have these looking glass or even proper understanding of proteomics, omics based technology, right? So we properly understand the profound impact post-thawed conditions can have. Now we know better, and that's what the field needed. We talked with our customers. They recognized this, but they didn't know what to do about it. So that's a perfect use case where we came up with a solution to meet the need. So to answer your question, this was there, but we didn't have the right optics and mechanisms to properly analyze the injury. Now we can with the advancement in the associated fields.
That makes sense. I'm imagining in any number of laboratories, the solution was to allow an army of graduate students to just constantly observe the cells until they were doing what they were expected to do, however many weeks that might have taken.
Exactly. So it is brute force to counter something that is non-optimal. And that's where we saw an opportunity. We from ATCC, being in the tech development side and development of strategically important products, we saw an opportunity right there and we went after it. Not everything works out, but this did work out really nice.
So you've spoken, you mentioned at least a couple times the optics and the genomics and the methods. Can you walk me through how ATCC achieved this solution? It's okay if you want to say no and protect the secret, but I'm curious.
Let me take a moment to think about how to best answer this question, because of course I do not want to talk too much about the intricate details, but it goes back to understanding cellular responses through omics, not only genomics. There are other omics technologies, metabolomics, proteomics. We looked at, well, we thought that, well, if an injury is manifested at the genetic level, that means that is profound. But there are other injury mechanisms that can get activated at the expression level, just transient expression level. And understanding those transient expressions through metabolomics or proteomics was very important in developing this technology, because then you can say, well, yes, this did get upregulated. This shows an injury response of some sort, right? And we can then take that information and bake it in the process of developing the technology. Are we getting somewhere? Did I answer your question?
I think so. I almost want to phrase it as, by taking all of these measurements, you could call them genomics, transcriptomics, proteomic measurements. It almost sounds as though we're doing the brute forcing ahead of time. Test everything, test every method, see what the impact is, the effect of it, so that by the time it gets to the laboratory, the brute forcing doesn't need to be done.
I would tweak that description. Yes, you are right. I tweak that description in a way that we are really trying to understand our products. We are taking time. We took time to understand our products, and we were thorough in understanding the injury response that cells undergo ahead of time. And we found the best approach given all the moving pieces in creating this product.
And that is simply by virtue, or I say simply, that is by virtue of the simple fact that we have at our disposal at ATCC innumerable ways that we can be measuring these effects.
Right. Right. So there we used our strategic management and essentially operations research concepts in identifying, well, what should be the best outcome, right? So yes, we used a lot of technologies. We did bring together a lot of technologies in the toolbox to create these next generation products.
Are there any technologies that you're anticipating coming to fruition? And I'm thinking anything from, new NMR techniques through more directly cryopreservation techniques. But any new technologies or breakthroughs you're anticipating could have an adaptation to serve this type of purpose?
Yes, as we work on developing technologies on these essential framework that I told you, that finding relevance for our customers, then convenience, the product should be really convenient to use. It should have a value proposition of saving time, money, and effort. And then standardization. We, being the standards organization, having many luxury of having many different products, we need to standardize things. But I want to quickly say something. We wanted to take a look at the entire application field, keeping an eye on the technologies that are coming up, new characterization technologies that are coming up, right? I think part of your question was directed towards that. You mentioned NMR. Spectroscopy as a field, understanding molecular behavior of a system at the molecular level, was a paradigm shift for biology, right? So we have seen that revolution, and more technologies are coming in. Raman, surface active technologies, surface spectroscopy techniques, right? Think about nanodrop, which was, nanoscale droplet and characterization using spectroscopy. These kind of technologies were not there before. But as we develop a product, we need to think about compatibility with the new techniques that are coming into the field of application. And also, we wanted to leverage these new technologies because people are going to use them as a looking glass to measure the system output. So we took a systemic view while we are developing these products, and these products of strategic importance.
It's exactly what I hope to hear, honestly. I think it's far too easy to get sort of tunnel vision on how a product is going to work or it's going to be received. Before we close out this episode, I also just wanted to sort of finish with, as far as the ThawReady cells or ThawReady product lines go, how many different options are available to the any consumer for ThawReady cells? Is it our entire catalog already, or have we focused on? I know you described the immunocells before. So what's the range of that, and how is that proceeding?
So we took. That's an excellent question. Essentially, when you have a technology, you need to think about that. Where do you apply the technology to have the most impactful outcome, right? So we went through this exercise, and again, we don't work in vacuum. I work with your group. I work with our cell biology product development group, and everybody together. It was a collaborative work where we weighted out different kind of approaches. Then finally, the one that was most appealing to me is that, well, if you prove the worth of a technology with the most difficult application, right, then you know that it'll work for easier downstream applications, right? That's why we went after immunogenic origin cells. THP1 is a very frequently used cell type in drug development, drug discovery. It serves a big portion of the biopharma industry. So that was the application. We have other products that are in pipeline, right, that are associated, and we are expanding that portfolio. So we are taking a portfolio approach to bring out the products in the market. Not everything is right away available in this format, because you have to think about the use case as also, right? Where you want to run your assay now, and if you wait for 7 days, you are risking infection and other things, or differentiation, right?
Right. Plus, I can't imagine this just immediately adapts with no further research necessary. And so that alone will take some time.
Yeah, I mean, it'll take time. We are all scientists. So, one of the cornerstones of scientific discovery and scientific product is really trying it out. So the products will get tested in the market for sure.
Well, with that, I'm looking forward to seeing that play out. I'm looking forward to seeing this portfolio expand further. Thank you again for your time. Looking forward,
Thank you.
more immediately, especially, to our discussion about the microquant next time.
Absolutely. Thank you.
The amount of time it takes to prepare a biological sample after freezing isn't strictly prohibitive, but it can add length to an already time-consuming process. Moreover, as Neil described, it can be destructive to the very material being used or analyzed. His team's ThawReady Cells aim to resolve both of those issues, streamlining the ability to use ATCC products more immediately and easily. In addition to the business case for faster uptakes, this spells fewer failed experiments, greater reproducibility, and overall more reliability in research. If that weren't impressive enough, we're not done with Neil yet. Next week, we'll be talking about the microquant system and what that delivers for biologists, largely in the context of regulatory frameworks.